Hello, I'm Roman, and welcome back to the series of the videos Neural Networks from scratch in Go. And I had to skip one day of recording because I wanted to finally finish one video I wanted to make for a long time on the main channel, and this is about how I deal with work and other things after I became a father. And this is why it's actually sometimes pretty hard to find the time to record stuff like this. So I would really appreciate if you take a look at the video, and yeah, I will leave the link into the description, and it should be shown right now somewhere here in the top right corner, but I'm not sure for the YouTube it not always work as expected. But for this series, I stopped last time on the implementation of activation softmax activation backward method. So we implementing all of the backward methods for our neural network, and the last one that kind of is left for the implementation, well, for the whole backward path, so we can calculate the lost, well, not the lost value, so we can adjust the weights properly, is the backward method for the softmax. And I started to dive into this in the last video, and probably this one will be short because today is, well, I'm recording on the Monday and it's surprisingly very busy day today, so maybe this video will be shorter than usual. So at least I will try to finish this part, and then, well, not sure if I will be able to start this one. Yeah, so let's see. So what we're going to implement, we need to implement this one, and I created a plan of what I need to do. So first things first, I need to allocate the D inputs same as the D values, and then we're going through, well, single output is the self.output. This is the output of the softmax activation function, and D values, so they should have the same shape, well, not the same shape, the same number of the rows. So what I'm going to do, so the first thing I need to take this, I will try to match the code as much as possible with the Python code, and then I can do some optimization. So the first one is I need to create a single output. And I cut my finger today, so it's pretty hard to type, but I mean, I will deal with this. So the first thing I need to take, well, the single output is part of the output. Okay, so the first one is I need to take the single output, and that's the part of the output, like this one. And if we take a look at the forward method, so the output contains from the rows that is equal to number of the samples, and the number of columns is equal to number of the outputs from the categorical cross-entropy loss, right? For example, if we take a look again at our model, yes, oh no, we're implementing the softmax activation function, so it takes an input as the output of the previous layer, so that will be equal to the number of the nodes from the layer, the one that we are applying the activation function. And so the number of rows is actually R is number of samples, right? So we're taking the first row, I think that should be, where is it, activation, Okay, I spent some time fixing the auto completion in the Vim. Not sure what was changed, but we can continue now. So okay, we're taking the activation output, and we need to take the first row. Well, not the first. We need to take row view, which is at index, right? Then we take in the single d value, which is the d values, again row view at the same place. Take row, okay. Then we need to reshape it. And the idea that, well, this flatten output array. And I need to do some testing. So for example, we have an numpy list p, was it p array 1, 2, 3. That will be an equivalent, and then we're doing the reshape -1, 1, and that gives us, well, the opposite. So for me, in my case, I think that should be, I think we can change it into single out would be like new dance. Okay. Which will be, I will take it. Okay. Okay, row. I don't need columns for right now. I'm going to single view. Very inconvenient to type without one finger. So single output, I would like to make a new dance for now. With how many rows? Oh, actually, that will be one, then call. Oh, no. That will be call. One, and we take in the row. Can I take the data? No. Wait, it's vector, so vector doesn't have this one. Okay, single output data and do it like this. Output row index, right? Then we create in this one and single output data. We're not transposing it, we're just reshaping it, because if we do the transpose, it will be actually the same, but in this case, but I will go with this one. So we have we convert it into the column vector. Then I need to calculate this one, and this is the interesting what will be the result. So the Jacobian matrix will be the matrix with, it will be two-dimensional matrix. So the first thing we need to understand the size, and the size, well, we need to understand the dimension, and the dimensions will be the same as the length of the values, and the length of the values is the single output, right? Single output has number of calls, so I would assume that we have new dense with call and nil. That will create new one. Then what we're going to do, we have the diag let output yeah, typing with a cut finger is a challenge. What we have, we need to get the result, so we're going to call diag flat from the values, which will be the single output which will be the single output data. Defined, word not used. Then we're going to have the dot product output, which will be, well, since the single output is already a column vector, so we're going to have the, and I think I need to, by the way, it should be the, yeah, so that should be the same size, because this is yeah. So the single output is number of rows with one column, and the single output transposed is one row with several columns. And in order to have a dot product, we need to have we need to fulfill the condition that number of the columns from the first one is equal to the number of the rows in the second one. So in our case, it will be again a square matrix. So it will be match new dense and same size. Then I need to call the actual product method between single output and single output t. Single out undefined. Yeah. And this is the one. Okay. So right now we should have, and I need to convert in order to use the go_num. I think I need to convert the flag row, and then I need to deac flag output as, I will optimize it later, but right now it's new dense with all and the data from this. It cannot use, yeah, I need to flatten it. Okay. I'm not going to change the implementation of this. Let's do it in a simple way. I in range, it's actually will be the range let, right? Or j in can range. What I'm going to do, I'm going to deac flag output set. I don't have set. Set ij, and the value is deac flag row from I from j. So then we have a copy. So right now the Jacobian matrix should be subtract the matrix B from A. So we have the deac output, and then we have the dot product output. Okay, I need to pick something. I have the all equal to len from single output data. So we still have the single devalues not used, and this is because I need to calculate the product between sample-wise gradient and add it to the array of the sample gradients. This is because I need to create a dot product between the Jacobian matrix and the single value. And the Jacobian matrix is square two-dimensional matrix when the single d-values is the one row array. Well, it's still we can treat it as a two-dimensional array, but it's one row, and again we have number of rows from the first one and the number of columns from the second one, which doesn't make any sense for me right now. Wait. Single value. Single d values. This is the one row from the d values. D values is the... So the Jacobian will be call by call. The d values will be samples by false, right? Call. So the result will be doesn't make any sense for me. We're going to store each vector in each row while iterating forming the output array. Wait. In the next step, we're going to iterate sample-wise over the pairs of output ingredients, calculating the partial derivative as described earlier. Storing the result vector in the input array. Okay, I will reread it once again. This raises a question: if sample-wise gradients are Jacobian matrices, how do we perform the chain rule with the gradient backpropagated with them? Also, what do we do with the fact that the previous layer, which is a dense layer, will expect the gradient to be two-dimensional array? Currently have a three-dimensional array of the partial derivatives. So this is the... yeah, this is what I calculated. The derivative of the softmax function with respect to any of its input return a vector of partial derivatives, a row from Jacobian matrix, as this influences all the outputs. We need to sum the values from these vectors so that each of the input of each of the samples will return a single partial derivative value instead. Because each input influences all of the outputs, the return vector of the partial derivatives had to be summed up for the final partial derivative with respect to its input. We can perform this operation on each of Jacobian matrices directly, applying the chain rule at the same time. Apply the gradient from the loss function using np.py. For each sample, it will take the row from Jacobian matrix and multiply it by the corresponding value from the loss functions gradient. So this is the... As a result, the dot product of each of these vectors. I'm curious why it's not transposed, because this is... I cannot test it yet, but we're going to iterate sample-wise over the pairs of outputs and gradients, calculating the partial derivative as described earlier and calculating the final product. The test ingredient array. Wait, maybe the d-values... Wait, what do we input as into the backwards of the loss? Maybe it's actually... I mean, that will be... maybe I'm just being stupid and there is no issue at all. How the d-values will look like? The d-values is the input... Oh, yeah. Okay, so the categorical cross-entropy loss is... of the d values is the array of the outputs. So this is the single line array, right? So it's actually not the row view, it will be the call view. And that will give us one value, right? So the result should be calculating the partial derivatives as described earlier and calculating the final product of the Jacobian matrix and gradient vector from the past in gradient array. So it should be like this. Okay, let's do as usual. So the first one is Jacobian matrix dimensions. The second one is this one, and that's single d values dimensions. Then the output, one that I'm going to store in the d input. Actually, before I do this, can I the inputs set? Can I set the row? Yes, I can set row. Okay, but okay, so the output in this case will be new dense between m, p, and again nil, because we're creating data. Then I need to do the product between Jacobian matrix and single d values. And then what I'm going to do, I'm going to take the activation, I need to take the inputs, I need to set row, and that should be index and output. No, not this one. Row. As usual, I will understand if I implemented it correctly once I will start testing. But yeah, I will double check the only thing. Yeah, so the d values, it's actually a one-dimensional array, so that's the vector of the values. And if we will take one thing, that should give us, so the p here should be 1. In that case, we will have the m equal to the number of rows from the Jacobian matrix, which is the equal to number of outputs from the layer. Then I have one value, which is the corresponding value for this class, let's say. But yeah, let me do. So I created the d inputs. I'm taking the number of rows for the value. So I'm going through all of the samples, and for each sample, what do I do? For each sample, we're taking the activations that we have for the softmax layer. Then we're taking the number. Then we're taking the probability for this index from the loss from the categorical cross entropy loss. No, wait. No, it doesn't sound right. I mean, the D values will have no. It should be row view. Then I don't get how we should end up here with one vector instead of, because maybe in this case I need to transpose it, because otherwise I'm taking the row view in both cases, row view, because we're passing so the D values will contain the same number of the samples and columns for the result probabilities, right? It means that if we will take the Jacobian matrix, which is a two-dimensional array, and the single D value is one row of the values, and in that case we won't end up with the dots. I mean, so it's single D values dot t, because in that case it will give us a two-dimensional array and one-dimensional column vector. So in that case we'll end up with one row, because in this case we'll have the dot product as two-dimensional. Maybe I'm missing something again. Okay, let me quickly double check and I will finish for today, as I unfortunately need to go. So I'm taking the from the output, I'm taking the single the row, calculating the number of columns, then we're taking the row from the D values. They should have the same size. I'm creating the single output from the single output data, right? And I'm reshaping it at the same time. So instead of having it as a rows, we'll have it as a one column with column number of the rows. Then what we're doing, we're calculating the Jacobian matrix, which is a two-dimensional array. It's a square matrix of the size of, the single output defines the number of the rows and columns. That will be the same. Then we're calculating the result. Basically, this is just a diagonal. Well, first we're creating the diagonal two-dimensional array, then we're creating the dense from it, then we're setting the value from the dark flat row. Maybe I will rewrite it just to return the dense already, but then what we're doing, then I'm creating the dot product output for this part, and that's the dot product between the single output, which is the column vector, and the single output transpose, which is the row. vector that will give us two-dimensional array again, so then we can do the subtraction. That should work. The only question I have is with this one. So I'm not sure, still don't understand how we end up with this one. Maybe there is a answer here. Well, no. Well, there's still a single devalues here like this. Okay, I'm not sure. I will continue tomorrow, but maybe I'll actually leave it as it is, because I mean, I implemented in a way that is described in the Python. Maybe the fact that I don't understand right now, it's not that important, and we'll see it actually works, and I will able to debug it. But I mean, I actually can test it. Okay, yes, I will start the next video from actually trying to call the backward method on the result. Well, I actually need to call the, yeah, I need to take the D inputs from the loss, and I need to pass it into the softmax, and we will see if the dimensions are matched. But for today, thank you for watching, and I see you tomorrow. Bye bye.